Okay, so we have already seen how the operational amplifier works. So now we just know that it tries to do everything to have the input voltage or the difference of voltages between the positive and the negative input to be 0, okay? And it does so because it measures the difference of the voltage between the positive and the negative input. And if this voltage is not 0 but positive, it will increase the output voltage and vice versa, okay? And that's why you have here the negative, because we want negative feedback. Okay. Now we assume that the operational amplifier is already working properly, so it has already arrived to the point where VD is equal to 0. So we know that if we wait long enough, the...
Oh yes, yeah, we learned about the slew rate.
Yes, so we know that the input voltage, or I keep saying input voltage, but I should say
terminal voltage.
The difference of the input voltages,
V delta,
VD, whatever, we can call it whatever you want, is equal to 0. Okay? Only if we know that we arrived to the point of equilibrium. Then we know that the current here enters it 0. Again, we are talking about ideal cases. So as a matter of fact, then we have some current, small current, which enters there, which is non-zero. Maybe we can see it later about the non-idealities. But now let's focus still on an ideal operational amplifier. And then also the current, let's call it I plus and this I minus, which enters in this positive input is 0. Now this is everything you need to know to operate with operational amplifier. Operate operational amplifier. Which means that once you apply this and about Kirchhoff laws and all other basic circuits theory laws, you can solve any circuit. Because it means that you don't know which is the voltage output here, but it will do everything to have VD equal to 0. So you impose these three conditions to your circuit, and then you solve everything else. So in the previous video, we have already seen how the non-inverting amplifier works. We have already demonstrated the output. So if somebody wants, go back and check in the videos before how the non-inverting amplifier works. Now, let's make the inverting amplifier. Okay? Can you do it yourself? Would you like to try? And V in is between what? Okay, so
wow,
let's impose
big.
Now. What?
Sorry, I made it super big.
Yeah, huge. Doesn't matter. Let's impose now the rules, okay? So the rules are:
no current goes in. No current goes in.
And then? Let's use another color.
Okay, yes. Oh, yes. VD is 0.
Okay. And that's it.
Yeah, and IO is 0 on the outer side.
Here the current now is 0, but actually it doesn't matter because...
Yeah, to what we're going to do, that is irrelevant.
You can have some load here and that's all fine. If there is a load here, and this is internally, you can see it like a source of voltage which is
controlled
by the difference of voltage here, okay? If this is ideal, so it has no output impedance, so here the current 0, then this voltage would be able to provide the current to this feedback to have exactly this condition. And it will be able to provide also the output current for the load. It's not always like that. They have some maximum current they provide. Operation amplifier, they have some maximum current. So if you put a load which is too much, it will absorb too much current, then it will not able to work properly anymore.
Yeah,
okay?
the effective gain will be reduced because there's no current that can produce the voltage.
There will be no current able to produce the voltage drop here to have this potential equal to this one. Okay.
Yes.
So now we don't care about the load. We are all fine with open output. Okay, circuit. Then, how do we start to solve this circuit?
Okay, well, we need to identify that there is current flowing through this.
Can I ask you one thing? Could you, when you draw the current, could you do it on the wire where the current flows?
Okay, so there's a current flowing here.
Okay, let's call it what?
II.
II. Okay, fair enough.
Then there's a current.
Can you? No, first let's calculate it.
Oh, okay. So II is equal to V in minus, and then we'll call this A.
A with respect of what? The ground.
Okay.
But you already have this voltage,
so
right?
0 minus, minus divided by the resistance.
Mm-hmm. So what we are doing is to consider
that loop.
That loop. In this loop we have V in, the voltage on the resistance, and then VD, correct?
Yes.
So V in is equal to VR plus VD,
yes.
Kirchhoff law.
Yes.
This is 0, so V in is equal to VR divided by 1, okay? So you can write here V in divided by RI. Cool.
Now I want to say that, okay, so there's no current flowing in here. So that means the current is flowing out, which what we call, IR.
IF. Okay. So
the reference
if you use Kirchhoff current, Kirchhoff current law.
KCL. If we're going to use KCL, we're going to say that
you know, when they say KCL, it reminds me KFC. Okay. So this node,
for that node,
we have this.
Yes. Okay. So now we need to describe II.
Slowly. Let's explain it to our friends at home.
II is equal to the voltage at the first node, which is VD. So VD is 0, so it's going to be 0.
Wait. Can you explain this to our friends?
Oh, excuse me. So there's current flowing in from whatever we are measuring, and then it flows through this resistor. Because of the rule of op-amps, no current flows into the terminals. Therefore, the only way for the current to go is up through the feedback resistor.
So here, there cannot be any current.
Yes.
No current here. So somewhere it has to go.
Yeah, and it has to go up.
It goes up. Okay. So IF is the same as II.
Yeah.
Okay. Exactly. Fine. So now I would say,
let's describe IF.
What do you mean by describe?
Well, we need to express it with respect to the voltage. Voltage over resistance.
I would say describe this. Can I describe this voltage? Let's call it VF.
Yes.
As a function of IF.
Yes. Oh, well, anyways, so the voltage here is going to be VA minus V out, but the voltage here is 0 with respect to ground.
Let's get to that point later. First, tell me how large is the VF. Okay? You know which is IF, because it's the same as II,
Yes.
and II is V in divided by RE.
Yes.
Okay? So, tell me, VF equal to?
VF is equal to?
RF times IF.
Oh,
You have a current flowing through a resistor.
II
Okay.
multiplied by RF.
II because
II is equal to IF.
so it would be IF, but we know that II is equal to
And then II is V in
V in
over RI
RI. So we substitute II with V
multiplied
input.
by RF.
Okay. And now we are almost at the end of the demonstration because
Then we can we just rearrange it.
of
So oh yeah, and then
we can demonstrate that V output is what?
well, we also need to state that VF is equal to V out.
No?
No.
Be careful. Take the loop. What do we have here? V out, then VF. Be careful, the current enters this way, IF, okay? II enters here, goes here, so IF has this direction, so the voltage drop is pointing in this direction, okay? So, and then VD equal to 0. So if I make a schematic, I have V out, VF, VD, okay? So write Kirchhoff law for this loop.
VD is equal to VF plus V out.
Mm-hmm. But VD is?
VF is equal to...
VF? No, okay, just write VF equal VF plus V out. Which means that V out is equal to V out is equal to negative VF, okay? Go away. So now we have that V out is negative VF. So let's write it here. It's negative because you see, as a matter of fact, if you put, let's use the colors, green and or better. Here you have purple and yellow. The purple goes here. The yellow goes here, but here there is zero difference of voltage, so it's the same potential. So this point and this point is the same potential. And here, the same potential. So if I give you plus and minus, plus is the purple and yellow is the minus, here I have the minus, and here I have the plus, okay? So it's flipped, the polarity. Here the arrow points at the plus, here the arrow of VF points at the minus, okay? So V out is therefore negative VF, and you know that VF is equal to?
V in over RI.
Okay.
So we can say that V out, wait, we're going to write this
No,
here?
write it here. Write it here. Negative VF is negative.
Negative 1 multiplied.
You really love to put this negative 1, right?
Yeah, it's not going to escape from those brackets. Actually.
Okay, so here we have the output voltage is negative input voltage times feedback resistor divided by the input resistor, okay? Cool.
And it's inverting because the signal is opposite to...
Okay, so for instance, you put input voltage of 1 volt, the feedback resistor will be 5 kilo ohms, the input resistance will be 1 kilo ohm, the output will be negative 5 kilo ohms divided by 1 kilo ohms.
Negative 5 volts.
5 times 1 volt is negative 5 volts. Okay? Again, the principle is the same. The operation amplifier feels the difference of voltages between the negative and the positive inputs of the amplifier, and it will change the output voltage until the current which flows here will create a voltage drop so that here the difference will be 0, okay? So if, for instance, I have here 1 volt and here 1 kilo ohm, the current here will be 1 milliampere, correct? Because we have 1 volt at the input. Here we have 1 volt. Here we have 5 kilo ohms. And then what happens?
So
here,
cancels.
yes, we can still see. Here you have 1 milliamp, right? Okay? Because we have 1 volt divided by 1 kilo. And this milliamp is in fact generated or absorbed. In this case, it's a negative current.
So it's going in the op-amp.
Sorry, this is, it's going inside by the operation amplifier. So, the operation amplifier creates a voltage, in this case 5 volts, so that, or better, it will absorb a current, and it does so by generating this voltage. It will absorb a current so that this current absorbed by the operation amplifier cannot come from here, so it will come from here. So it's the same current which will flow from the source. So the moment the operation amplifier generates a voltage which makes the current be 1 milliamp, then you will have 1 volt here, and this will be 0, okay? So it will start generating 1 volt, and then it takes less current. 2 volts, 3 volts, 5 volts. The moment it creates 5 volts, the current will be 1 milliamp, and then if there is 1 milliamp here, it means that the voltage on this resistor, the voltage drop on this resistor will match the voltage there, which means that obviously here the voltage will be 0. And then it stops. I say, fine, I have sucked the correct current to have this voltage drop equal to the voltage at source. And therefore you get 0 voltage, okay? This is important because, again, people think that this is a short circuit. It's not. It's a virtual short circuit in a sense, because there is no connection between these 2 points.
Yeah,
I just create
it's imposed.
It's imposed by the rules of the circuit, okay?
But it's not actually connected.
It's not actually a short circuit, okay? So again, the ear is feeling some voltage, and it will adjust the output until the resulting current will make a voltage drop equal to the voltage source, and then the difference of voltage between the different potential between the terminals will be 0. Okay?
Yeah.
Cool. And this is everything. Like, you can solve any circuit using these rules. Okay.
Okay.
Do you want to make another circuit?
Yeah.
Do you have another circuit?
Yeah, I have differentials.
Okay.
And integrating and differentiating.
Let's start with the integrator.
And then we got a input resistor. And then we got Vn, Ri, Cf. And this goes to ground.
Ah, yes, don't forget. This is a typical mistake. Not when you make a circuit because you see it. Well, actually, I remember, probably I said these things 20 times, but there was an episode of the Big Bang Theory where on the board of Sheldon Cooper there was the circuit, not inverting, but without that. And they were writing the equation of the inverting amplifier.
Really?
Yeah, without the ground.
Oh, well.
I said, fuck, it doesn't work. So.
I don't think anything worked about that show.
Yeah. Anyhow, so no, but the point is that when you do it in real life, like connecting the things, it's very easy to forget about that. I don't know why. Fine. Again, the rules is the same. So try to solve it. So do exactly the same things as before.
Okay, so we need this one.
Colors.
Okay. We're going to have an I called II. And this is rotating in this loop. Okay, and in here we have Vn. We're going to have VRI. And then
maybe move in that direction.
We're going to have Vd.
Okay.
Vd is 0, as always. So Vn...
Why do you put VRI in this direction if the current goes this way?
Oh, it's opposite, excuse me.
Okay.
So Vn minus VIR, VRI is equal to 0.
Okay, so again, VRI is equal to so II equal VRI divided by RI.
Yes.
So maybe write it here that we have some space. Still you have to write it in here.
Okay.
Okay, so II equal...
Oh, you want me to express II?
I want II, of course. So VRI divided by RI, fair enough. VRI is... No, wait. It's V input divided by RI. So, sorry. VRI is V input. So you can write it instead of VRI, again, V input. Because we have...
Yeah, I know. So...
So this is like saying that VRI is equal to V input, okay?
Yes. Yes.
Okay, so
now
V input, this is equal to V input divided by RI.
Yes.
Okay, fine. So we have this voltage here. Since the voltage between the negative and the positive input is 0, the same voltage that we have here is the same voltage on the resistance, and therefore we can calculate the current which goes through the resistance, which is the input voltage divided by Ri, okay? By the way, I will just say it now because maybe it's obvious, but for some reasons, people see input voltage, input resistance, input voltage, input resistance, and they always think that is Vin divided by Ri.
No, because there's another voltage source.
No, because there is this net. If I have a resistance here, for instance, R star, and then, well, in this case, yes, because there is current here, okay? But you have always to to solve the circuit, okay? So you must always make the Kirchhoff law. Now in this case, it's a bad example because in this case, this is zero.
Yeah, that's zero.
So
it's
the
same.
voltage is zero, voltage is zero, is the same. But generally speaking, it's not that the input resistance, the current is always Vin divided by Ri. It is because here we have zero voltages, and therefore we can say that this voltage is equal to this one. So only if this point, let's call it point A, has the same potential of the ground, then you can claim so, okay? And you can say that this point is at the potential of the ground only because here there is no difference of voltage, okay? So here you have the ground that you have here also. Okay. Now I will erase this resistor, which is at this stage useless. It has some advantage though, but we can see it another time. Fine. Cool. Now the current, so we have some current which comes from here. The current goes through the resistor, it arrives here, and then once it arrives at this node,
goes through the capacitor.
Goes to the capacitor because, of course, it cannot enter in the amplifier. Here, the current is zero. So once it arrives here, it cannot go to the amplifier, it goes to the... And what happens to the voltage of the capacitor?
Yeah, no, this is something I can't
Let's
remember.
use another color.
So VC.
So let's make VC. Do you have a blue?
Le bleu.
Ah, I have it in my hand. So let's call it VC or
VR.
VC as a function of time. The voltage on a capacitor is think about that. How do you build a voltage in a capacitor?
You charge it.
You charge. How do you charge it?
By applying a voltage. Or by...
The voltage is a result of...
providing a current.
So you provide a current.
Yes.
You send charges.
Yes.
And because the charges go there, they build up a voltage, right?
Yes.
So the more current you give, the more
voltage there is.
you develop, okay?
Because the more current the more current you give, the more charge there is,
which means that you have a bigger electric field,
a bigger potential,
a bigger voltage, okay? So it will be the integral
of the current
from time
0
to time
t.
1, so that's or time t, okay, fair enough. From time 0 to time t of
the current
dt.
Yes.
Okay.
Need to remember that.
Plus
C.
No,
V0.
Plus the voltage at the time t0, okay? It's an integral. So you have the starting condition. If you start from the starting condition with 0 because you have a switch here. Let's say that you have a switch. And
so the cap shorted in...
You short it. And you, maybe with some resistor, not like that.
Yeah, not dead.
Because if you close the capacitor, just move a little bit so the rest is not.
Sorry.
So if you have a capacitor and you force the voltage to be 0 with the switch, it means that you need infinite current to go away suddenly because you have a step of voltage. We have 1 volt there, and in 0 seconds later you have 1 0. But how can the voltage go from 1 volt to 0? You have to take out all the charges
at once
in no time, which means that you need infinite current to bring out all the
yeah, and it warms the capacitor up. And
so you want always to limit the current which exits. So you can never impose a voltage straight to the capacitor directly. You cannot impose a voltage to the capacitor.
You have to charge it.
You have to charge it. So you put some current and you develop a voltage, okay? Fine. But we know this current, right? is
It's II.
IF,
Okay, IF.
which is
II.
also II. Okay, but you know II because it's this one. So plug it in.
Okay, and we assume it's 0.
Yeah, let's assume that it's 0 and that's it. So now don't forget that this voltage is generally
a function of time.
A function of time. So we have, maybe I will rewrite it with white chalk so it's more visible because this is our final derivation. Okay, maybe also this one. So V out. Ah, wait, no. This is VC.
Yes.
It's still the voltage on the capacitor, which is 1 over C.
The integral
from T0 to T
of V in T
of the input voltage
over Ri.
R is a constant, so as a matter of fact we can take it out.
Yes, we can.
No problem.
1 over Rc.
dt, okay? Now, the trick is the same as we saw before for the inverting amplifier. So we see that this output voltage here, move a little. So this output voltage here is negative VC. Because again, you have a green? If you take this loop, I'm really not sure that is going to support your weight. So you have V out, VC,
V in.
Nah.
Oh, VD.
VD.
So it's 0.
So this is 0
minus VC
minus V out, which means that V out
is equal to minus VC.
Minus VC. Okay, so you just apply Kirchhoff to this loop, and you get that V out is equal minus VC. We know VC, so we can, like, let me write it here, so we have a nice expression. So V out is negative VC, which is negative 1 over input resistance C, the integral from T0 to T of the input voltage dt, okay, plus V0, whatever, okay? So the output is equal to the integral of the input. Cool. No problem whatsoever.
There we go.
Actually, now that I think about that, let's go back for a moment. So is it clear, this one?
Yes.
Okay. Let's go back a moment to the inverting amplifier. Okay. We have our input resistance, you have the input voltage, you have the ground, you have our feedback resistance, and you have your output voltage. Sometimes you will find a capacitor here.
Yes.
Okay? Why? What happens if you put a capacitor there?
Well, we saw previously that it integrates the signal.
Think it, this stage, don't think about the time domain. Think about the, like if it was in a phasor, okay?
It would create a delayed response.
What happens if you have high frequency? What is a capacitor for high frequency?
It's a short.
It's a short. Why? Because you have XC is what?
1 over 2 pi c. J.
J is if you have Z. Z is
for impedance, yes.
so.
Okay, so we're in a scalar value, pardon me.
So 2 pi f, sorry. 1 over omega c, okay?
Yes.
It means that if you have high frequency,
xc approaches 0.
x is going to 0.
Yes.
It means that for high frequency, this is a short, which means that
it will saturate at a high frequency.
Not saturate. It will just. What is the output voltage here? Remember, is if you call this VF, is negative VF,
yes.
Correct? But what is VF at high frequency now?
0.
0. So at high frequency, you have the reactance of the capacitor, which is going to 0.
So
it will drop down.
So it's a low-pass filter, this.
Yeah. So it will cut away the high frequency.
Yeah, that's what a low-pass filter is, right?
Yeah.
Okay, yes.
So a low-pass filter will let. So of course, if the frequency is.
Yeah, low-pass, yes.
If you have low frequency, then X is going to be infinite, okay? Because if you have 0 here, this is infinite. So it's like open, okay? Then nothing changes. So if you put here a capacitor, it will reduce, it will suppress the high frequencies. So very often, if you have a lot of shit at the input, you have a lot of frequency at the input that you don't want, and you want to cut them away, and you have a simple inverting amplifier like that,
okay.
And there is a lot of high frequency disturbance, all this sort of jazz, and you want to remove them, just put here a capacitor, and the output will not show you this frequency. So you will not amplify the high frequencies. You will amplify only the lower frequencies.
So now let's say I want to get rid of a 1 megahertz frequency. What frequency would I put in the equation of XC?
Sorry?
Okay, so there's frequencies near the 1 megahertz range that we want to attenuate or we want to get rid of, right?
Okay.
So
you have to make your calculation with the resistance and the capacitor.
Well, couldn't we just put some sort of frequency value in XC and then put that in there and then we know when XC will start?
I don't know now. I don't have on the tip of my tongue how to calculate it.
Okay, but it's not going to be exactly 1 megahertz if we're trying to get rid of 1 megahertz.
No. It's a low pass filter. So at some point you will have going down. So your gain
cutoff frequency,
and you have a cutoff frequency as before.
Okay.
So at the end, still it's a low-pass filter. So very often, if that's the point, if you have for instance, if you have a very high speed, very high bandwidth operation amplifier, and it's too large for the bandwidth that you need, and you need, so it will amplify also high frequency that you don't want.
Yes.
Well, you could choose another operation amplifier which is not so good, let's say good, so fast, which doesn't have such a large bandwidth. But if you have that and you have to use that, how can you reduce the bandwidth artificially below the bandwidth of the operation amplifier itself, if you don't need all of that?
With the bypass.
With the capacitor, which is in fact sometimes easier because maybe you have that operation amplifier. Sometimes when you make projects, you can use only certified components which go under a lot of tests and so on for emissions. So especially, for instance, if you make medical devices, it's extremely hard to certify components for medical devices. So you cannot just pick whatever you want. Yeah. So you have the operation amplifier. You need to use that. You design your circuit and you say, fine, I know that I need only this bandwidth because the signal is going to be till that bandwidth. But there is always some noise. So how can I cut it off? Just put a capacitor and Bob's your uncle. Okay. So it will avoid having large noise at the output and so on. Okay, so it's really slow down. So this is one. So
the low pass filter.
This is an inverting amplifier together with the low pass filter, so it will amplify only the low frequencies. Okay. Okay, another circuit you want to study?
Differentiator.
Differentiator or differential amplifier? What do you mean?
Both.
Okay, so let's.
Because a differentiator will give you the derivative, the change.
Okay, so let's make a device which has as an output the derivative of the input. Okay.
Yes.
Okay.
So let's analyze what's happening in this loop. So we have KVL. We have a voltage on Vn. We have a voltage on Vc. And we have 0 volts at Vd. Therefore, we can say that Vin minus Vc is equal to Vd, which is 0.
Maybe it's better if you use the white chart because the red one is not totally visible.
Well, I can see that. I can see the green one, yeah.
Okay, never mind.
But it basically looks white, so I'll just continue. So should I just stay with the red one? Or just white?
White. Stick with the white.
Okay. Okay.
So the voltage on the capacitor.
We need to know that there is a current coming from...
man, put the current in the wire where it flows.
Oh, pardon me, I'm sorry. There's IC.
I see.
There's also going to be IF. Okay. So we saw in the previous example that...
Draw also VC. VC on the capacitor.
Oh.
Okay.
Okay. So now we need to describe the voltage on the capacitor.
Okay.
So VC in the time domain is equal to 1 over RC, which is usually the time...
No. Only C?
No, just C. Jumping. And the integral will be from 0 to t of the current. Okay.
So this means that the current is the voltage. If the voltage is the integral of the current, it means the current is the...
Voltage. What?
No.
Sorry.
If the voltage
is
obtained by performing the integral of the current, it means that the current is equal to what?
The derivative of the voltage.
Okay, so...
So this implies that IT is equal to 1 over C dV over dt.
Are you sure it's 1 over C?
Thank you.
Okay, fine.
Theorem.
So the current is equal to the capacitance times the derivative of the voltage.
With respect to time.
Fine. And now you know how to calculate the current, right?
Yes.
No, sorry. You know which is the voltage on the capacitor. Voltage on the capacitor is equal to VC is equal to this voltage, VC, is equal to this voltage, right? Because this is 0.
Yes, yes.
So, right,
Oh,
VC is equal to V in, which is, in fact, something that you had already written here, okay? VC
yes.
is equal to V in. So, you can say that IC is equal to the capacitance CI times the derivative
Of V in.
of V in with respect of time, okay? Because it's the voltage on the capacitor, but the voltage on the capacitor is the same voltage of the input, okay? Then this current cannot enter in the operation amplifier, so it will be to the current in the feedback, fine. So we can say also this is the current in the feedback. Fair enough. Now, V output is equal to what? Let's take this loop. We have V feedback, V output, Vd, which is in fact 0. So V output, if you apply Kirchhoff to that loop, are you sure?
No, it needs to be negative.
So you made some mistake somewhere.
It's 0.
0.
It's minus.
And then?
Another minus.
If you take
oh, yes.
this as a positive, okay, so. If you take this as a positive direction, always, maybe it's always useful to write down like
the direction.
The direction. So this is positive. So whatever has the same direction is positive. Whatever is going in the opposite direction is negative. Okay. So here V out is equal minus VF, which means minus this is VF. VF is the voltage on this feedback resistor.
Wait.
Fair enough. Maybe continue here. Minus 1. VF is IF. So IF is C.
Yes.
Derivative of V. So you plug in, instead of VF, you plug C times the derivative of the voltage, input voltage. And then you get an output, which is RF. So in some sort of, in some sense, you still amplify it because you still have here a resistor. You put a bigger resistance, you have a bigger output voltage. Okay, the current which charges this capacitor is still the same. Okay, but then this current is forced to go through the feedback resistor, and the bigger is this resistor, the bigger is going to be the output. So you still have some resistance here which amplifies. Amplifies what? The derivative of the input. Okay. Now, before going to the differential amplifier, I will propose this very simple circuit. Actually, I want to do two simple circuits. The first one is the so-called voltage follower.
Oh, yes.
Okay, so this is pretty simple. because you know you have plus input voltage,
and then
negative.
I is directly fed back.
It goes directly to the output, okay?
So whatever voltage is on the input will be on the output. Except the reason you would want to do this is if you have a source that can't, if you have a voltage source that can't provide that much current.
Okay, because the current here is
0.
0. So if you have any
Something very small like a thermocouple.
Any source of voltage, thermocouple, whatever, okay? You just don't want to load the source, okay?
At all.
So this is the internal resistance of the load. Let's say that...
Of source, excuse me.
Sorry. So this is... This is our box. We connect... These are the terminals. This is our black box. And so we connect this to the ground. We don't want to take any current out of that, okay?
Yeah, at all.
So what you do is to put the this voltage follower, which means that there is no current getting here. The voltage here will be 0, which means that if you apply Kirchhoff to this loop, you will have V in. Okay, let me do it better.
V in is equal to V out minus 0.
Exactly. So, but, you know, I know that you are smart, so now you got it.
Yeah, I know.
But let's help our friend at home.
Oh, we're going to draw the loop.
VD and V out, okay?
And then the loop.
And then it will be something like that, okay? So this is positive.
So V in.
V in.
Minus VD.
VD.
Minus V out.
Minus V out.
Equals 0.
Is equal to 0.
VD is 0.
This is 0.
So then V in
is equal
to V
out. Okay? So whatever is the voltage that you have here, you have it there. But it doesn't suck any current. So it has infinite input impedance. Okay? Because whatever is the voltage they apply here, there is no current. And the only way you can have 0 current, whatever is the voltage that you apply, is because you have an open circuit. Okay? So whatever is the current there, let's say that you have here a load. Whatever is the current going to the load, because here you produce, I don't know, 2 volts. You have 2 volts at the input. You will have 2 volts at the output.
But now you can source a lot more current.
So if you have 1 kilo ohm, okay, you will have 2 volts divided by 1 kilo ohm, 2 milliamps. So here you get 2 milliamps, okay?
Yes.
But this 2 milliamps comes
from the op-amp. Not
from the op-amp?
Not from the source.
And where does it get the current, the op-amp?
Oh, from the voltage terminals in the op-amp. Well, not in the op-amp. The op-amp is also powered. And it will get the current and the voltage from...
So far we forgot to mention that the operation amplifier doesn't work by the power of the Holy Spirit.
Yes.
But it works because
it's connected to a source.
To source. So let's say that we have, I don't know, plus 15 volts here, negative 15 volts.
Or ground. Sometimes it can just be 0.
Sorry?
The negative terminal can sometimes be connected.
Yeah, we can discuss about that in a moment. Now, so in this case we have a positive current. So it's going to take this current from here and it's going there, okay? Now, it's true that, generally speaking, you cannot reach directly this voltage terminal. So the maximum voltage that you can have at the output will be Vs or minus Vs if it's a negative voltage. So if you have here 15 volts and minus 15 volts, the output could be plus minus 15 volts. It cannot produce 30 volts, 20 volts. because where does it get it from? Okay.
Yeah, there needs to be a source.
There should be some source somewhere. Actually, you don't arrive really to 15 volts.
Yeah, it's clipped just below 15.
Just below. There are some amplifiers which arrive almost to the rail of the supply, but
there's a voltage drop internally.
There will be some minor voltage drop and so on.
Because of the
so that's why, in fact, you can,
transistors.
If you know that you are amplifying only positive, well, in this case, there is not amplification, there is just follower. So you know that you can connect this to ground, okay? But you must know that then you can only have positive voltage here. You know that it will be from the input from ground to plus 15 volts, actually ground, a little bit, almost ground, not real ground. So technically there is nothing preventing you to connect it to ground, as long as you know that it will limit the range that you can operate it. What you can do, let's say that you have, I don't know, a voltage which is going positive and negative.
Oh, okay? You can create an offset.
You can put an offset.
Sorry, I jumped. No one's going to know what we're talking about.
No, but
if you have a swinging voltage and you only have a positive supply voltage, what do we do?
So, for instance, let's say that you want to amplify. So you have an inverting or non-inverting amplifier or inverting amplifier.
That doesn't matter.
Okay. So what you can do is to create. So let's say that this is the
source.
And you can move, instead of putting it to ground, this point, you can
change its reference.
You can put it like if this is Vs, you can move this point with the voltage divider to another potential. So you shift the signal up. Because this is maybe would be interesting to see the differential amplifier, because this is in fact the point where you can see what happens if you have different potential at the positive. Okay. So one thing you can do is that. But before going to the differential amplifier, there is another circuit I wanted to talk about. Okay. This is something that probably you remember it. We saw it in the laboratory.
Okay. Summing amplifier.
Let's say that we have a source of current, which is rather small. Okay. Photodiode. You have a photodiode. So there is the light going there, and it creates some current, okay? Because when the photons arrive to the photodiode, they give the energy to the electrons to jump to the other side and circulate, okay? So if the photon has energy large enough to make this process happen, then the energy makes the electron jump on the other side, so that you have some current will circulate, okay? So we connect the photodiode. Again, I try to explain it in a non-very technical words, but just to understand what's going on, okay? So you have the light, you have some little current from the
diode,
photodiode. Let's call it high F. Then, what is the output? Let's say that here we have, I don't know, 100 kilo ohms. Can you find the output? Where's this current going? Here, cannot enter, right?
Okay, so the current is going here.
Okay.
So then, I for plus IF is equal to 0.
No.
No?
Not with this direction.
Oh, minus.
IF, so
is equal to IF.
the current from the photodiode is equal to IF, okay? Then, what is the voltage here? VF.
It's going to be V out over RF.
Sorry?
VF is going to be...
VF.
Oh, excuse me. Is going to be IF multiplied by RF.
Okay. Which means that IF is equal to the current of the photodiode. Okay. So the output here will be the current of our current source, in this case the current of the photodiode, times RF, in this case 100 kilos. So if I have here, 100 kilo ohms. So if I have here, I don't know, 10 microamperes, here I will have 10 microamperes times
100K.
100 kilo ohms, which is
10. 1
volt. Okay. Well, this is 10 to the minus.
Wait, let's just do it like this. Sorry.
Okay, look. This is 10 to the minus 6.
Then it's going to be...
this is not 10 to the minus 6.
Micro.
Yeah, but this is 10.
Aha. So then that's 1 to 10 to the minus 5.
5, and this is what?
This is going to be 4, 5.
Yeah. 5. It's 1. Okay. Cool.
Yeah.
Fine. So you take a current, you send it to the feedback, and then you get a voltage, which is the Ohm's law. You have 10 micro, small current, but you send it to large resistor, boom, you get a decent voltage.
Okay.
So what we are doing here is nothing else than taking this current and sending through a resistor, correct? Now, what I'm asking you is this.
Yeah. Okay.
Why don't we simply take this photodiode? Where shall I write? Here or there? Here.
Ah, there's space everywhere.
Let's take this photodiode and connect it directly to this resistor. And then we take the voltage here. Oh, wait. The current is this. The current still goes here.
Yeah, so there will be a voltage.
Sorry?
There will be a voltage.
And the voltage here, let's say V out, again, V out is definitely going to be RF if there is no load here. We don't connect any load.
Yeah,
times I. So Ohm's law is there, still applies. Oh, sorry, I forgot this is a photodiode. So there is some light coming to the photodiode. So still...
So the question is...
Still you have this voltage output, which is equal to the current that you want to measure times this big resistance, okay? Still 100 kilo.
Yes.
What's the problem? So why the hell we should put an operation amplifier with a voltage supply and all the mess, the cost and so on, when you can simply connect the photodiode to the resistance?
I want to say that the impedance that the photodiode will see here is RF. But the impedance the photodiode will see here is infinity.
Is what?
It's infinity.
Is what? What is the impedance seen by that?
Infinity.
You're right, sorry.
So, therefore, this will have, this will
No.
This will not affect it.
It's not infinity, sorry.
It's not?
No? What is the input impedance that you see here?
Infinity.
No. What is this voltage?
0.
0. So,
But it's virtual.
still, from the potential point of view, is 0 the voltage there.
So?
So it means that it sees a short circuit.
But wouldn't a short circuit mean all the current would just be synced? Synced down?
But the current, instead of going here, goes there.
Yeah. So basically, the photodiode is seeing nothing in.
It's seeing at 0 impedance.
But 0.
If there was infinite impedance, it would mean, if there was
Infinite impedance.
It would mean that the current is 0, right? Infinite. So this is.
Oh yeah, you're right. You're right. Yeah.
Is
so,
0.
Oh my God, yeah.
If you have infinite, so input impedance, which is infinite,
no current would flow.
There is no current.
Yeah.
Okay. So here, because I see this virtual short circuit, it means that the virtual short circuit, it's true that it's virtual, but it means that the voltage between this point and this point is 0. So it means that you have 0 voltage difference between these 2 points, which means that this point is at the same potential of this one, which means that it's the maximum current I can get out of the sensor. Okay? So in this case, you're right. You're getting RF.
Yeah, it's loading it.
It's loading it.
And it's ultimately
not loading, sorry.
It's affecting it.
It's affecting it in terms of that you cannot have the same current because you are in the middle, in a situation which is in the middle between these 2 extremes. Here you have infinite input resistance, which is seen by the photodiode. So you get 0 current because it's open. Here you have short. So 0 input impedance. So here is the maximum current that you can get. Here you are somewhere in the middle. So you have a current which is not so much because in fact you have 100K, so quite large. So as a matter of fact, what you want to do, if you want to get the maximum current out of your sensor, you need to short it, right? Because if you short this source of current is the maximum current you can get.
Yes.
And how do you short it? By putting this point at the same potential of this one. And how do you do it? By using this operational amplifier. Okay.
Yeah. Okay. So the electrons will race to 0, but it won't go. It will go through the RF.
Exactly. Now, of course, this current then it cannot go to the operational amplifier. This is just imposing the voltage to be the same.
Yes.
And therefore to suck out as much current as possible. But then the current will go to here, and they will go to the operational amplifier.
And that opposing force is from the actual.
But then the voltage here is created by the operational amplifier.
Yeah.
So it's not the photodiode which creates the voltage. The task, the dirty job, is done by the operational amplifier. The operational amplifier is in charge to creating the voltage in such a way that the current here will be equal to the current here, and therefore this current will generate an output voltage equal to the current times the resistance.
Understood.
Okay? Yes. So this is the advantage of using, in this case, the operational amplifier, because you convert a current into a voltage. You convert a current into a voltage, and you do so without affecting the source of current. Okay?
Yes.
So this is one important thing that you can do with operational amplifiers. So before going to the differential amplifier, just a simple circuit that we can watch. Okay. You have a resistance.
Ooh, okay.
You have something like that.
And we're going to drive it.
This is your load. This is, I don't know, RA. I don't have much fantasy. You do something like that.
Oh, wow, okay.
Not so difficult. Now, again, let's apply the same rules. So we know that the voltage here is
0. So
zero.
VD is 0.
So what is the voltage on the resistance RA?
0. Yeah.
Kirchhoff to this loop.
Excuse me, it's going to be VD minus VA.
So V in. Let's use this positive.
Oh, excuse me. V in minus VD minus VA equals 0.
So VA is equal to
Negative VN. No, VN.
Vn, okay? So the voltage here is equal to the voltage here. But look at that. It's this voltage. This finger goes here. It's the same voltage as this, okay?
Huh.
Look, it's the same. Same voltage. So the current here, let's call it IA, is
V in divided by RA.
V in divided by RA, okay? Now, I ask you, which is the current in the load? The current in the load is, look at Kirchhoff current at this node.
Well, we're going to be here, right?
No, this current is the current.
0, that's 0.
0, so this current equal to 0, just move a little. If this current is 0, this is the current of the load.
I'm going to say VS minus...
No. You know how much is IA, right?
Yeah.
And write Kirchhoff at this node.
Okay, give me a second.
Look at this node. There is no current here. So the current
yeah, this current load. Okay, excuse me. So I load is equal to 0 plus...
IA, simply. Even without watching Kirchhoff, you would see that if the current of load comes here, it cannot go to here because it must be 0. So it must be
yeah.
It must be definitely equal to IA, which is equal to V in divided by RA. Okay.
Got you.
So this is interesting because the current in the load is proportional to the input voltage, independently from the resistance of the load. So it does not depend on the load. You put one here, 1 kilo ohm, fair enough. The operation amplifier will generate a voltage V out large enough to pilot this transistor in such a way that it will provide this current, okay? In fact, you can calculate the voltage here let's call it V prime. V prime will be R load plus RA times IA, which IA is equal to I load and IA are the same, so the same current flows through these both resistors. So you have this voltage plus this voltage, correct? So the voltage on RA is RA times IA. The voltage on the load resistor will be R load times IA, which is the same of the current in the load. Therefore, you get what? IA is V input divided by RA, and Bob's your uncle. Now, you can calculate this. This is the voltage necessary to have here a current which flows in this resistor equal to this current, okay? So, the operation amplifier will generate the necessary output voltage so that the transistor will generate this voltage here and have this current. This is an ideal current source. Why? Why this is a current source? Because for any load, so here, if you change the load, instead of 1 kilo, you get 10 kilo ohms, you will change this voltage, but you will still have the same current. Let's say that here I have 1 volt, okay? 1 volt, and here I have 1 kilo ohm, okay? So the current will be 1 milliamp, okay? So the current here will be 1 milliamp. So let's make a better summary. Let's say that the input voltage, which is this voltage here, is 1 volt. And let's say that RA is 1 kilo ohm. Therefore, the current in the load will be 1 milli, because we have 1 volt here. The operation amplifier brings the same voltage on this resistor because there is no voltage here. So you have 1 volt divided by 1 kilo ohm, you get 1 milli. And the same milliampere flows through the load. Okay? How large is the voltage? Well, it depends on the load. Let's say here we have 1 kilo. 1 kilo, so you will have V prime will be 1 milliampere, which has to flow through 1 kilo of the load and 1 kilo of A, okay? So it will be 1 milliampere times 1 kilo ohm plus 1 kilo ohm.
The voltage will rise.
So it will be 2 kilo ohms times 1 milliampere, 2 volts, okay? What happens is if instead of having a load of 1 kilo, you have 2 kilo ohms, okay?
How is the voltage input affecting the circuit?
In which sense?
I don't see the voltage input at V prime.
Oh, the voltage, sorry, because I said that the current IA is the input voltage divided by RA. Okay, so you have this voltage, input voltage.
So that voltage will determine the current?
Yes, here, look.
Oh, it's, so you control the, oh yes, yes, okay. Voltage controlled current source.
Voltage controls current source, yeah. Because your voltage is imposed to be the same voltage on the terminations of this resistor. So there will be a current here, which is only input voltage divided by RA. And it doesn't depend on the load, okay? whatever happens in the world, the current here will be always 1 milliamp because you apply 1 volt here, and RA is 1 kilo.
It's dependent on RA and VN.
And that nothing else.
Yes.
So what if you change the load? You change the load and you have 2 kilo.
It will self-balance itself.
It will create another voltage. So now you will have 1 milliamp times the load. Now is not 1 kilo anymore. It's 2 kilo. Okay. RA is 1 kilo ohm still. So you have 3 volts. What if the load becomes, I don't know, 10 ohms?
It'll be 10 volts.
10 ohms, not
10 ohms. It will drop.
So
it will be 1.1 volts.
10 ohms. I have 1010.
1.001 volts.
Okay.
I think
so. I have 1000.
1010.
1 milliamp times 10 ohms.
1.01.
So it will be 1.01 volt. Okay. So you can you will have always 1 milliamp here if the load changes. So the current does not depend on the load. It depends only on the current, on the voltage input that you decide. You decide to have a current of 1 milli, fair enough. Put 1 volt here, 1 kilo ohm here, and you will get 1 milliamp. Okay? It does not depend on...
Yeah, it's not affected by the load.
It's not affected by the load. So it's a perfect current source because it gives you always the same current that you decide independently on the load that you have. Of course, if the load becomes too big, it will require too large current, too much voltage, and therefore it will it will not be able to. Why I put here a transistor? Just you could directly connect it to the operation amplifier, but then it would need to require this current. If it's 1 milliamp, it's fine. If it's not, if it's too large the current, then the operation amplifier would not be able to provide this current. Okay. So what it does is to give a little base current here, but the current will coming from the source. Okay. This is just to show that if you want to create a current source with larger current supply, you need transistor so the current comes from here and it doesn't come from the operation amplifier if the current that you require is too large and cannot be provided by the operation amplifier. Okay? Yes. But for small current, if it can be provided by the operation amplifier, fair enough, you can avoid the transistor. Okay.
Yeah, I've never seen the circuit before.
Okay, but very simple. Very simple.
Yeah, makes sense. Understand it.
Let's now go to the differential amplifier. Here, try to draw the differential amplifier, and let's see how it works. Mm-hmm. I would say let's go directly to the specific case. Because generally speaking, these 4 resistors have different values, okay? But in reality, if you want so you want it to have these 2 resistances, let's say R1 is, I don't know, 1 kilo. Kilowatt potatoes. Ohms, fair enough. And let's say RF is 10 kilo ohms. Fine. So let's solve this circuit. Difficult?
Yeah.
Actually, it's not, as long as you use the, how do you say it in English? When overlap the effect, like principle of superposition? Superposition, okay. When can you use the superposition effect and what is it?
Well, the superposition effect is when you have multiple sources in a circuit and you can replace a voltage source with an open line and a current source with a closed line. Opposite, excuse me.
And then what do you do?
So let me just repeat it. You have multiple sources. You replace the voltage source with a closed circuit, and you replace an ammeter with an open line.
And current source.
A current source with an open line. You then solve however many circuits you get out of this. And then I can't remember.
Okay. Let's try to understand what happens.
You join them somehow.
Yeah, so you have multiple sources. So in that circuit, you have, for instance, in this case, we have 2 sources of voltages, V1 and V2, okay? And both of them will affect the output, okay? So what we say is, okay, let's turn off V2.
And only solve it for V1.
Yeah, so.
Okay, so we're going to create 2 circuits.
Turn off V2. And let's solve it. Let's see the effect of V1. And then we do the opposite, okay? What does turning off a voltage mean?
You short it.
V2, 0. Okay? We turn it off by saying that the voltage is 0, which means closed loop.
Yes.
How do you turn off a current source?
You cut it.
You open it. Because a current source gives current. If you open it, no current. So if you have a current equal to 0, if you turn off the current, means current equal to 0, which means open, okay? Fine. So let's turn off V2 and let's watch the effect of V1 to the output, okay? The effect to the out. You can do it there directly. Turn it off. Turn off V2.
V2 is turned off.
Okay, what do you have?
This is completely shorted now, so this doesn't exist.
If it's shorted, means that the current here is
0.
0. So the current here
0.
0. There is nothing here.
Okay, so we shorted it out. Therefore, the voltage at RF is 0. The voltage at R1 is 0. Therefore,
and what is the voltage here?
0.
0.
Okay.
So what are you left with?
We're left with an inverting amplifier.
It's just an inverting amplifier. The only difference is that instead of having the short circuit between the positive input and the ground, you still have a couple of resistors there.
So case A, V out is equal to -1 times V in multiplied by RF over R1.
Write it a little bit bigger. Otherwise, I'm afraid they're not going to see it. Times V in. Excellent.
Okay.
Now, opposite. So we turn off V1, and we watch what happens to the voltage output because of V2. So let's take again our differential amplifier. And we shut down V1, which is going to be 0. We take only V2. We have RF, RI, RI, RF. And let's calculate the output. Okay? Now, first of all, we calculate this voltage, okay, which is V plus. Are you okay? So V plus, in this case, keep in mind that you have 0 current here. So as a matter of fact, it's like if you have V2 with 2 resistances, like this, Ri and Rf, and you want the voltage on this one. So what you get?
Voltage divider.
Okay.
Okay, so V plus is going to equal V2 multiplied by Rf over R1 plus Rf.
Rf divided by R1 plus Rf, okay? So we keep it here. It's gonna be useful.
It will be.
Then,
okay,
V minus is equal to V plus, okay?
Yep.
This is V minus, and because there is no difference of voltage between these 2 points, between minus and negative and positive input, V minus is equal to V plus. This means that this is a little bit tricky because people think, okay, I shut down V1, and therefore the current is 0.
No, but V out is going to make it.
There is a current, but
in the opposite
direction. The opposite direction. Because it's not a current which comes from V1, but it's a current due to the fact that here is not this point at 0. This point now, it's at V plus voltage, and now this point is at 0. So it's reversed.
Okay.
Usually we have V1 and this point to 0, but now it's reversed. So now you have a current. This current, let's call it I. And this current is given by V minus divided by R1, which is equal to V plus divided by R1, okay? Now, this current, is there any mistake? No. Now, this current cannot come from the operation amplifier, from the negative input, so it's the same current
from RF. So
from
RF is equal to I.
So now we have a current which flows through RF and goes to R1,
okay,
which causes a voltage drop. Let's use yellow. VF, and VF is what? Let me erase this part, otherwise
it's going to be V out minus V.
Wait. VF is this current.
VF is I over R. I multiplied by RF.
RF. But I is V plus divided by R1.
Okay, so it's going to be V plus multiplied by RF over R1.
Fair enough?
Yes.
Okay. So, now let's watch at this loop. I will maybe erase this V negative because it's just messing up everything. Okay, so I will consider this loop. Okay, here we have V plus. Then we have
VD.
D.
Up, yes, and then V out, up.
Then we have VF.
Okay, pardon me, VF.
And then we have
V out.
V out. Okay. Now we know that VD is equal to 0. So V out is equal to V plus plus
VD.
VD is 0 plus VF. Okay. You know that this is going to be.
Yes.
So V out is the sum of VF plus V plus plus VF. Okay. Now, but we know that VF is equal to RF divided by R1 times VF.
Yes,
okay.
Yes.
So I will just go down here. So it's
V plus.
V plus plus VF is sorry.
God.
Let's write it somewhere there because I'm old and I cannot go down on my knees. So V out is equal to what? V plus
VF.
So this voltage plus VF.
So that's
but we know that VF is equal to
IR?
V plus times RF divided by R1.
Yes.
Okay? So it's V plus plus RF divided by R1 times V plus. Which means that, I don't know if they can see, yeah, maybe your head. Maybe I should continue here.
No, don't worry. Sorry.
So it's 1 plus RF divided by R1.
Multiplied by V plus.
Okay? Fair enough?
Yes.
Now, it's maybe better to write this as R1 plus RF, correct? Because you have R1 divided by R1 is 1.
Oh, yes,
and
yes, of course, yes.
It's just a way to write it down.
Yeah, you simplified it. Well,
at this stage, it's convenient now to take the expression of V plus and plug it there.
Okay.
Correct? So you have R1
plus RF
plus RF
over R1
over R1.
Close it.
Times V2
multiplied
times RF divided by R1 plus RF. Okay? So here we have R1 plus RF divided by R1 times V plus. But we know that V plus is V2 times RF divided times R1 plus RF. So now this part will be simplified. R1 plus RF,
yeah, so it's V2.
They cancel out. So V output is going to be V2 times RF
over
R1, which, if you think about that, is the same voltage we obtained before with the inverting amplifier, but without the minus. So, if we summarize all the results, I will just erase everything. So is it clear?
Yes.
And this happens only because we chose properly these values.
Yeah, yeah, if they're not balanced.
If they're not balanced, this trick doesn't work anymore. You cannot simplify all these things, okay? So we had two sources, V1 and V2. Here is RF. Here is R1. R1. RF. Here we have V out. This is V2. This is V1. Okay. Now, if we have V1, the output was, you remember, negative. It's
RF over R1 multiplied by V1.
Times V1, okay?
And then
if you have V2, V out
it's just V2 RF over R1.
RF divided by R1, V2, correct?
Yes.
So the
How do we add them?
Sorry?
Carry on.
Yeah, say it.
Oh no, I just said to myself, how do we put these together?
Well, this is where the superposition effect comes into the games.
Yes.
Because they say, okay, if you have different sources of voltage or current in the circuit, study the circuit like if you have only one. Then each result, you calculate the output,
yes.
and then you sum up the effect of each generator. Because then when they will work together in the same circuit, this first generator will cause this portion of the out. This other generator will cause this portion. If they work together, you sum up the effect. So the final V out will be V out, let's say 1 and V out 2, V out 1 plus V out 2, which means V out 1 is negative RF R1 times V1. V2, V out 2 is RF divided by R1 times V2.
So RF over R1.
So it will be RF divided by R1 times
V2 minus V1.
V2 minus V1.
Wow.
So we have an output which is proportional to the difference between these two voltages.
That's insane.
Why?
I don't know, that was just...
What does it mean?
Just deep.
Okay. So, and of course we amplify it. So, again, we have an output.
We amplify the difference.
We amplify the difference. So, we have an output, again, which is proportional to, in this case, the difference of the voltages. But not only that, we also amplify it, because if you use, I don't know, 10 kilo ohms for the feedback resistance and 1 kilo ohm for the input, you get the output which is 10 times the difference of the input, okay? This is the advantage of having a differential amplifier. When can you apply this principle? Be careful, it's not always valid, this principle. This principle of the superposition of the effect, because it's based under one assumption. You can use it only when the system is linear, as long as the system is linear. Why? Because what does linear mean?
The change with respect to the dependent variable, the independent variable.
You have input and output, okay?
Yeah, the input will always result in an output that grows in an even manner.
Proportional.
Proportional manner, not even.
So let's say that
it grows by a factor of x.
This is the input.
Yes.
This is the output. And you have a linear characteristic. It could be also offset, but it should be linear.
Yes, as long as it's a straight line.
Now, systems have a range of linearity. They are not,
they're not
linear in all that range. For instance, in that case, you know that we are powering our operation amplifier with plus minus 15 volts. Mm-hmm. And you know that you cannot produce 20 volts. Okay, you have some limits. So let's say that at some point it saturates. Also saturates here. Now, the first effect give you, so the first input gives you an output of 1 volt. Okay? So you go here, and the characteristic tells you that you get 1 volt. Then, the second input will give you 4 volts. You sum the effects of the first and the second input, and you get
5 volts.
5 volts is your output.
Okay.
So you will be here, okay? But what happens if the first, and that's fine, you are in a linear range. That's why you can sum the effects. You sum the first, you have the first effect, gives you 1 volt. You sum the second, you have the second effect, you get 4 volts. You sum them up, 5 volts. Everything is hunky-dory. But then, what happens if the inputs are larger? Okay. So again, we have the same characteristic input, output, and again it saturates, I don't know, at 15 volts. Now the first one will give you, the first input will cause an output of 10 volts. The second will cause, so you repeat, you shut down the first, of
12 volts.
12 volts. Now, if you sum up the effect, you will be to
22 volts.
You would be here at 22 volts.
But no.
This is not valid anymore because we saturated 15. So you can use this trick of study the effect of the first source, second source, and then sum them up only if, when you sum them up, you're still in the linear region. In this case, we are in a region where it's not linear anymore because you cannot produce 22 volts, okay? So be careful. This trick of using the superposition effect, the principle, is only valid, it works only if, when you sum up all the effect, you're not over...
Yeah, you're not getting out of the region of the amplifier.
Exactly.
Operating region.
Of the linear region, okay?
Yeah.
So be careful about that, this effect. You can use it always, but as long as you're not going out of
the region
of the linear range, okay?
All right.
So let's have another break.